I'd like to talk about a topic that's really important as it relates to organic molecules, and it is the topic of acids, bases, pH, and then also buffers, because pH is something that's really important to the functioning of organisms. We have to maintain particular pH so that our organic molecules have the right shape and do the things that they're supposed to do. So I want to first start off talking about acids. What makes an acid an acid? So an acid is a substance that when you put it into water yields a hydrogen ion. And hydrogen ions tend to be very, very reactive, and so this creates the consequences of acids, and so this is what burns the skin or burns hole in your clothes, things like that. An example would be hydrochloric acid, HCl. And when you put HCl, hydrochloric acid, in water, it will dissociate to form a hydrogen ion and a chlorine ion. So the chlorine ion is just not necessarily defining what an acid is. The fact that it dissociates to form a hydrogen ion, that's what makes the acid the acid. Now, bases or alkaline substances are those that when we put them into water, or at least this is how we're going to define a base, as one that when you put it into water, it will yield an OH ion, known as a hydroxide ion in water, or will absorb H+. Hydroxide ions, like hydrogen ions, are very, very reactive, and then again can burn the skin and cause other kinds of problems. And an example would be sodium hydroxide, NaOH. And so when we put NaOH in water, it will dissociate to form a sodium ion and a hydroxide ion, the OH ion. So again, it's that OH ion that's defining it as a base, at least in our primary definition here. Now, one of the things that's interesting about acids and bases is that if you combine an acid and a base, you have a very reactive substance and an acid, a very reactive substance and a base, and you might think if you put that together, you'll have an incredibly reactive substance. But what happens is they tend to neutralize one another. So when you combine an acid and a base, they form some type of a salt and water. And so in the case of hydrochloric acid and sodium hydroxide, if we combine hydrochloric acid, sodium hydroxide, we'd end up with NaCl, which is our common table salt, or the common salt that we normally eat, and HOH, or H2O, which is water. Now, when we look at acids and bases, we define them according to what's known as a pH scale. And so what the pH scale is trying to tell us is it refers to the potential of hydrogen ions. So it's really hydrogen ions that are going to define the pH of a solution. And also there tends to be an inverse relationship between hydrogen ions and hydroxide ions. So if you have a lot of hydrogen ions, you have relatively few OH ions or hydroxide ions, and vice versa. So we basically define acid and base solutions according to this pH scale. So when you look at the scale, if the number is low, and this is actually a negative log scale, so the lower the number, what that means is the more hydrogen ions it is. So the scale runs from above 0 to 14, so 0 plus to 14. So the closer we get to 0 then, the more hydrogen ions there are in the solution, and the fewer hydroxide ions there are in the solution. At a pH of 7, we describe this as a neutral solution because at pH 7 you will have equal concentrations of hydrogen ions and OH ions. And then as we move above 7, the hydrogen ion concentration gets lower and the hydroxide ion concentration gets higher. So for above 7, we can generally consider those basic solutions. Below 7, we consider those acidic solutions. And at pH 7, we consider that a neutral solution because the hydrogen and OH ions are exactly the same. And again, if we have equal concentrations of H and OH, they will combine together to form water. So as we look at pHs if we were looking at these numbers and trying to describe them, if we had a pH of 3.2, that would be an acid solution. 7.4 would be a weakly basic solution. 14.8, that's a trick question because 14.8 is not on the scale. So 0 to 14 would be on the scale. So this would be a trick question if I were to do something so horrible. 13.7 would be a strongly basic solution. 8.0 would be a weakly basic solution. 5.5 would be a weakly acidic solution. 1.7 would be a strongly acidic solution. So as we look at this scale then, if I were to ask you which of these is the strongest acid, hopefully you would notice that or come up with the fact that 1.7 is the smallest number, so that would be our strongest acid. If I were to say which is the strongest base, Again, hopefully you realize 14.8 is not on the scale, so that would be a trick question. So that would make 13.7 then our strongest base on this scale. But also it's important to understand that really any solution can be defined as an acid or a base. So another way a question I might ask you looking at these numbers is if I said, okay, which is the strongest acid, you would say 1.7. But what if I said, which is the weakest base? The weakest base. So that would also be 1.7. So 1.7 is not only the strongest acid, it's also the weakest base. 13.7 is the strongest base and the weakest acid. So we can really define almost any solution in terms of acidity or basicity, but generally we look at 7 as being the boundary, below 7 as being an acidic solution, above 7 being a basic solution. Now, pH, like I said, is really important, especially in complex organisms like ourselves. We will have organic molecules that work best at particular pHs. And so it's important to maintain those pHs. And so the chemicals that will maintain the pH in a particular solution, those are known as buffers. So the role of a buffer is to maintain the pH of a solution, to keep it at whatever pH it's at. And in our bodies, around 7.3 is where we want our blood pH to be. Anyway, the H+ concentration, the hydrogen ion concentration, determines the pH of a solution. So what we want to do in a solution is keep the hydrogen ion concentration consistent. If we can keep that hydrogen ion concentration consistent, it keeps our pH consistent. And generally, buffers are weak acids that maintain pH by either binding or releasing hydrogen ions. And we're going to look at an example of that here in just a second. So an example of a buffer is carbonic acid. Carbonic acid is a weak acid. And as we look at this equation here, you can see that carbonic acid, H2CO3, can dissociate to form H+ and bicarbonate, HCO3. So it can go in this direction. But the H+ and HCO3 can combine to reform carbonic acid. So the solution can go to the right, it can also go to the left. And really what determines that, what's going to happen is the abundance of hydrogen ions. So this is a weak acid, meaning that it will not, 100% of it will not dissociate. Only a certain percentage of it will dissociate. And what determines the percent dissociation really is the pH of the solution. So I'm going to be using some diagrams to represent this equation too, to make it a little bit easier to understand what's going on. And so this will represent H2CO3. So the black is carbon. These are our hydrogen ions. So H2, the black is our carbon. And then the 3 oxygens. So H2CO3. The bicarbonate, HCO3. The white circle will be a hydrogen ion. OH will be an oxygen and a hydrogen together, of course. And then water would be the 2 hydrogens with an oxygen. So if you need to refer back to this, that's going to be our key for the little diagrams that we use. So diagrammatically looking at this, as well as showing the chemicals in, so we have carbonic acid, which can dissociate into hydrogen ions and bicarbonate, and those can reform to form the carbonic acid. And so again, kind of looking at this without all of the arrows and so on, carbonic acid under certain conditions will dissociate, forming a hydrogen ion and bicarbonate ion. And under the other conditions, the hydrogen ion can bind back to the bicarbonate, reforming carbonic acid. So again, it can dissociate, it can reform, depending on the conditions. So let's go ahead then and look at a couple of situations. If we have carbonic acid, and that's our buffer, what would happen if we added an acid to the solution and a base to the solution? So first, let's look at what would happen if we added a base to a solution that had carbonic acid in it. So in our solution, we're just looking at a small part of the solution. The solution has a particular pH. What determines the pH of the solution is that we have a certain number of hydrogen ions free in the solution. So we're just going to look at this, and in this small part of the solution, we have 2 hydrogen ions free. So at the end of this process, we want to make sure we have 2 hydrogen ions there as well. And that will mean then that the pH has not changed. So if we add a base to the solution then, what would happen is we'd be bringing in an OH. And if we bring in OH, OH and H+ have a strong affinity for one another, and so they will form water. Now, water, of course, is not a problem, but what has happened to our hydrogen ion concentration? It's decreased. Because one of the hydrogen ions bonded to the OH and formed water, we now have a change in the number of hydrogen ions. That means now we have a change in the pH of the solution. And what's the function of a buffer? It's to maintain the pH of a solution. So what will happen, what carbonic acid's response is to that, since there's been a decrease in the number of hydrogen ions, that will cause one of the carbonic acids to dissociate and release a hydrogen ion. And in so doing then, that gets us back to the original number of hydrogen ions and maintains the pH of the solution. So let's go ahead and look at this one more time. So if we add a base, we have a solution with a specific number of hydrogen ions. We bring in an OH. OH will react with one of the free hydrogen ions to form water. That changes the pH of the solution, decreases the number of hydrogen ions, and so that will basically drive that reaction to the right. Carbonic acid will release one of its hydrogen ions in response to that, maintaining then and getting us back to the original pH. Now, one thing that should be obvious though is that if you keep bringing in OHs, eventually it is possible you will use up all of the available carbonic acids, and at that point then pH would change dramatically after that point. So you have a certain amount of buffer in a solution, but if all of that buffer is consumed, after it's consumed, pH can change. But as long as you have enough buffer in the solution, it will maintain the pH of the solution in this way. So now let's look at carbonic acid and what would happen if you added an acid to a solution. So if we add acid, we're adding hydrogen ions to the solution. So again, we're starting off with 2 hydrogen ions. At the end of this process, if we want to maintain pH, we need to end up with 2 hydrogen ions. So if we add an acid, we add a hydrogen ion. That's changed the pH. And so what that will do is cause one of the hydrogen ions to bond with a bicarbonate ion, reforming carbonic acid. And then that gets us back to our original pH with 2 hydrogen ions in this case. So again, one more time, if we add an acid, we're adding a hydrogen ion. Hydrogen ion in response will bond to bicarbonate, reforming carbonic acid. That gets us back to the original pH. So that will be the role of the buffer here. But again, if we eventually depleted and used up all of the available buffer in the solution, then the pH would begin to change dramatically. But as long as there's adequate buffer in the solution, it will maintain that pH. So maintenance of pH is really, really important then, because a lot of organic molecules, particularly proteins, their shape is dependent upon the pH of the solution. If the pH of the solution changes, those molecules begin to change their shape, their function changes, and that can literally lead to death. So if your blood becomes acidic or overly alkaline, that can be a lethal condition.